Alright, this video is going to be on graphing sine and cosine by hand. And we're going to do it two ways. We're going to do algebraically and then actually graphically, like doing it visually. And you can choose the way that works for you. So first we're just going to review the transformations and what they look like in these graphs. And you should be familiar with this because you did learn it last year, but we just want to make sure that you still remember everything and what it all stands for. So here, instead of talking about a vertical stretch or a vertical compression, we talk about the amplitude, and I will define that in a moment. But the amplitude is similar to what you guys are used to. So the absolute value of A, if it's greater than 1, then that means it's being stretched, right? If the absolute value of A is less than 1, and really it'd be between 0 and 1, then it would be a compression. And if it's negative, then we are just reflecting the graph over the x-axis. Now this part right here, I was thinking about how I really wanted to write this, and I decided to write it this way so that you guys would really be intentional about thinking about it as you approach these problems. So whenever we look at this, the number in front of x, as we talked about before, is a horizontal stretch or compression, and here we're not going to call it that, we're going to call it a period change. But you have to be really careful to factor out the number that's in front of the x. So here, before we can talk about the transformations, I have to take the b out. So I'll divide the b out of there, and then I have to divide the b out of the c value as well. So it's going to be c over b. And you are probably not going to see it notated just like this in other resources, but that doesn't mean it's inaccurate. It's still accurate. It just means that I want you guys to really think it through. So I want your notes to look like this. So this value for b is going to tell us the period of the graph, and the period of the graph is just how far it takes to do one full cycle. So it has to do with the left-right measurement or an x value for the graph. But anyway, if we have the absolute value of b is greater than 1, it's going to be a compression. So the period of the graph would be smaller than usual. And then if the value for b is between 0 and 1, it's going to be a stretch. And we're not going to talk about these being positive or negative here because it honestly would not make a difference. Anyway, well, much difference. Okay. This part right here, anytime, just like before, if you have something in the parentheses, that tells you a left or right movement, and it's the opposite of what you would think, kind of like how these transformations are the opposite of what you would think. And then the number on the end is still up and down, and it's still kind of exactly what you would think. All right, so for a definition, the amplitude is how far it goes, and by it I mean the curve. So we could say how far the curve goes from the midline. And we'll discuss that more once we actually get a graph on the paper. And a typical amplitude, if there is no stretch and no compression, a typical amplitude is 1. The period of the graph is how long it takes to do one full cycle. And a typical graph would be 2 pi. We would start the curve and then go through the cycle and end the curve at 2 pi. All right, so a note, something I always want you guys to keep in consideration as you graph these, is we are always going to graph 5 points for one period of the graph, and then copy those 5 points for a second period. So you graphing the first period is just what I expect every time you graph, and then you copying those 5 points and doing a second period of the graph shows me that you understand how to extend the graph and keep the pattern going. So it's important that I see you do both of those things. Okay, so for example number 1, we're going to do it 2 different ways. We have y equals 3 sine of 2x. And first thing I want to look at is the transformations. And when you do transformations, it is not uncommon to always just want to know the amplitude and the period, even if they have not changed. And in this particular case, they have both changed, but even if they have not changed, we're going to find them every single time. All right, so the amplitude here is 3. This is vertically stretched by 3, so if it normally has an amplitude of 1, this one is going to have an amplitude of 3. And then I forgot to add something in your notes, so let's go right back up here. The way that you calculate the period of the graph is you're going to say the period of the graph is the same as 2 pi, because that's a normal period, divided by b. So 2 pi divided by b, you might circle that or highlight it or something, because we're going to often do that formula. So here, if we want to know what the period of the graph is, we're going to do 2 pi divided by 2, and so the period of this graph is pi. So again, you guys remember it's the opposite of what you would think. So this kind of looks like we should be horizontally stretching the graph, but we're not. We're actually going to do the graph in a smaller period of space than we normally do, so this is actually horizontally compressed. And then that's it for my transformations. I don't have any more there. Okay, so next what I'm going to look at, since we're doing this algebraically first, is I need to know what my 5 points are for the typical sine graph. So if you look at your unit circle, when we do the typical sine graph, we're going to look at 0 radians, pi halves radians, pi radians, 3 pi halves, and then we're going to go back to 2 pi. So those are all my x values because I'm doing sine of that angle. And then since we're talking about sine of an angle equals a value, if I'm looking at sine, I should be looking at the y-coordinate. So that is 0, and then up here we have 1, 0, -1, and back to 0. So sine of 0 is 0, sine of pi halves is 1, sine of pi is 0, sine of 3 pi halves is -1, sine of 2 pi is 0. Alright, next, I'm going to go ahead and we'll see if this will make your brains explode or not. I'm going to go ahead and do both of these transformations at the same time. When we practiced doing transformations this way in previous units, we did things one at a time, but I'm going to see if we can do more of those and do okay. So if you guys recall, the 3 means that we're taking the y-coordinate and multiplying it by 3. Over here we divided by 2 to find the period, so we should be taking the x-coordinate and dividing all the x-coordinates by 2. So I'm going to go ahead and do that first. 0 divided by 2 is 0. Pi halves divided by 2 is pi fourths. Pi divided by 2 is pi halves. 3 pi halves divided by 2 is 3 pi fourths. And 2 pi halves divided by 2 is just pi. And if that's too much to do in your head, you could always do like pi over 2 times 1 over 2, and pi times 1 over 2, and 3 pi over 2 times 1 over 2. So if you write it out off to the side, kind of showing your work, then you can see how those would all simplify. And then I'm going to take my y-coordinate and multiply it by 3. So 0, 3, 0, -3, 0. So at this point I've done all the transformations. All that is left now is I need to draw the graph. So I know that my y value needs to go between -3 and +3. So there's -3 right there, there's +3 up there, and I'm going to go ahead and just draw the positive x-axis here. So you can kind of think through, how should I label my intervals so that this is the most convenient to draw? And since it goes by fourths, I'm just going to count 1, 2, 3, 4 pi, 1, 2, 3, 4, 2 pi, like that. All right, so we've got 0, 0, and then at pi fourths we've got 3, at pi halves we have 0, at 3 pi halves we've got 3 pi fourths we have -3, and then at pi we have 0. And I'm making sure that I have a nice smooth curve there. And then I'm going to go ahead and continue the pattern for a second cycle of the graph. And I make sure to draw arrows at the ends to show that this is going to continue on. Alright, so right here, I'm just going to label a few things right here. This is the midline of the graph. And then you can see right up here, this is the amplitude. So that's an amplitude of 3, an amplitude of 3. So when we talk about amplitude, we're never going to say that something has a negative amplitude, because an amplitude is a distance. It's how far you are from the middle. So amplitudes are always positive. If you have a negative number in the front, you're not going to say that it has a negative amplitude. You're going to say that it has an amplitude of that number, and then you're going to say it's reflected over x, because that's what that means. And then here, this would be the period of the graph for this particular example. Okay, next I want to show you how you could have done that same graph but not drawing the points out like this. So we're going to do it just graphically and not algebraically. So here, if we were to do it graphically, then it helps to have a little sketch of sine, just your typical sine graph, off to the side of your paper. So we're going to just graph, here's 1 to -1. So a typical sine graph looks like this. That's just like the standard sine graph, no transformations at all. That comes from the values on the unit circle. So then if I'm using that same example, then in my head I think, okay, it has an amplitude of 3, so I need it to go to 3 instead of 1. So 3 and -3. And then I know it has a period of pi instead of 2 pi like normal. So here's how I graph these. I have noticed that the pattern for sine is that it starts at 0 and it ends at 0 and it hits 0 in the middle. And then I know between these first 2 points it goes up to 1, and between the second 2 points it goes down to -1. So on this one I'm going to say, alright, my period is from 0 to pi instead, so I know I'm going to start at 0 and end at 0 for the period. I know that halfway in between those it hits 0. And then I know that typically halfway in between those it goes up to 1, but I have an amplitude of 3 this time, so I'm going to go up to 3. And then I know between these it has an amplitude of -3, so I'm going to go down to 3. So yes, it is a lot faster to do it by graphing. However, if your brain does not work very well this way, then it's not smart to do it the quicker way if you can't get them right. So if your brain does not catch on to this very well, then you should do it algebraically, because it just makes more sense to practice the right thing than to practice the wrong thing. Okay. I apologize in advance for how long this video is probably going to be. I'm sorry. I just want to give you guys some good examples of, at this point we're going to do examples of some weird problems so you guys can see how those go. Okay, so the transformations here, again, we're always going to start off with amplitude and period because they always want to know what those are. So the amplitude here is 1/2. Remember, it cannot be negative because there's no such thing as a negative amplitude. So that negative there means we're going to be reflecting this over the x-axis. And then the period of the graph on this one is kind of weird. Off to the side we'll show our work. So it's 2 pi divided by pi thirds. And if you guys remember how to divide that, we do keep it, change it to multiply, and flip the other one up. And then here, those pi's would cancel, and we would just have 2 times 3 is 6. So this graph has a period of 6. There's not even a pi involved in that graph at all. Okay, and that takes care of all the transformations. So now we're going to look at the original points for y equals cos x. And we're going to start with the same radians that we did before for our 5 points. But this time from the unit circle, we are not going to look at the we're not going to look at the y coordinate, we're going to look at the x coordinate this time. So we've got 1 and 0. And then we've got 0, and then we've got -1, x coordinate, and then 0. And then at 2 pi, we're back to 1. Okay, so there are the 5 points that are important for a cosine graph. Alright, so next what I'm going to do is I'm going to go ahead and just take care of that period change. We can go ahead and do this one in a couple steps. That is not what I meant to do. Did her pen just erase? That's so cool. Okay. So I know that my x value is going to be the value that's changing. So I'm going to take the current x value and I'm going to multiply it by 3 over pi. So that's just 0. Pi over 2 times 3 over pi. The pi's would cancel and I'm going to get 3 over 2. Pi times 3 over pi. The pi's are going to cancel and I'm just going to get 3. 3 pi over 2 times 3 over pi. The pi's are going to cancel and I'm going to get 9 over 2. And then 2 pi times 3 over pi. The pi's cancel and I just get 6. So again, I just thought of it the way that I did here, where I had 2 pi divided by pi over 3, and I flipped those up. And so that fraction that I had flipped up and multiplied, that's just what I was using to convert all of these here. Actually, let's go ahead and let's just do all the transformations all at once. We might as well. So y equals -1/2 in the front. So now that means I'm going to take each of my y coordinates and multiply them by -1/2. So 1 times -1/2 is -1/2, and 0, and +1/2, and 0, and -1/2. And then again, we want to draw a graph where it's going to be easy for us to get all of the parts in there. So since I'm doing halves, I'm going to go ahead and scale my y-axis bigger this time. As I'm sure you guys could guess, we want to be careful to always label our x and our y-axis on these, because you've noticed like this graph is labeled drastically differently than the last graph that we did. So if you do not label your x and your y-axis, there's nothing I can do when I grade it to make sure that it's accurate. Alright, 0, -1/2. 3 halves is the same as 1.5. So 1.50. 3 +1/2. That's the same as 4.50. And then 6 -1/2. And we're going to make sure that we continue the pattern here, and that when we draw this graph, we're drawing it curved. So, and when you draw your arrows on the end, please do not draw it so it looks like it's going straight down, because it's not. It should be going back up. So a cosine graph starts in a different place than a sine graph does, but it's going to ultimately look the same. Alright, so that was algebraically. We're going to go ahead and do this one graphically now. So the first thing that we want to consider is what a typical cos graph would look like. So a typical cos graph starts up at 1, and then it crosses through 0, and then it goes to -1, and crosses through 0 and goes up to +1 again. That is a typical cos graph. So here, if we go ahead and start drawing this out, I'm going to go up to 1 and -1. So I know based on the information above that the new period of the graph is 6. So here is pi, here's 2 pi. So if the graph is a period of 2 pi, then I start up at 1 and I end up at 1. And I hit -1 exactly in the middle. So for this one, I'm going to say, all right, I should begin and end from 0 to 6. But since my amplitude, or the thing in front, is telling me -1/2, instead of starting up at 1 and ending up at 1, I'm going to start at -1/2 and end at -1/2. And then halfway in between, we're on the other side of the graph at 1. So for us, halfway in between, we're going to be on the other side of the graph at positive. And then halfway between those 2 points, we cross over 0. Halfway between these 2 points, we cross over 0. So we cross over 0 and cross over 0. And then we can just continue that pattern. So start and end in the middle, and then in the middle again. Always making sure to draw arrows to show that our graph is continuing on. Okay, I'm sorry, I would stop the video there if I could, but we have to look at one that has a vertical and horizontal shift. So this is the last example. I promise. I owe you guys cookies or something. That's a lie. I'm not going to make you cookies, but wasn't it a nice thought? Okay, so on this one, the transformations, we're always going to start off with amplitude and period. So the amplitude of this one is just 1 because there's no other number telling us it should be different. But I do have that negative there, so I'm going to say we are reflecting over x. And then for the period, we have to factor out that 3. So x minus, and if I take out that 3, I have to think 3 multiplied by something is going to give me pi halves. And so the thing that would do that is pi 6, right? Because if I multiplied 3 times pi over 6, that would give me pi halves. So if I divided by 3, then pi 6 is what I have there. So the period of the graph, off to the side, we're going to say 2 pi divided by b. In this case, b is 3. So that means the period of the graph is 2 pi thirds. And then we also know we're going right pi 6, and we also know we're going up 1. Okay, so I'm taking my original sine graph, so 0, pi halves, pi, 3 pi halves, 2 pi. And you don't have to memorize those y-coordinates of the point, because you can just steal them from the unit circle every time. So memorize them or not, it doesn't really matter as long as you have the unit circle to refer to. Okay, so now I'm going to go ahead and do the transformations next that require multiplying, because we always multiply and divide numbers first, and then after that we can add and subtract, and that goes back to what we know about order of operations. So the amplitude and the period and the reflection are the things that I can change right now. So I'm going to do the negative and the sine of 3x right now. So I know that each of my x coordinates has to divide by 3. So 0, that would be pi 6, pi thirds, 3 pi 6 would be pi halves, and then 2 pi thirds. And the negative tells me that each of my y coordinates are going to change signs. So 0, -1, 0, 1, 0. Okay. Now that I've done that, I just have to do one more set of transformations where I actually get all of this stuff in. So sine 3x minus pi 6. Oh, plus 1. Okay, so my x coordinate is going to move to the right pi 6. So I'm going to add pi 6 to all of those. And I'm going to go ahead and cheat this a little bit. Maybe not. Yeah, I'm not going to. Okay, pi 6 plus pi 6 is 2 pi 6, which is pi thirds. Pi thirds, oh gosh, this is terrible. 1/3 plus 1/6 is pi halves. So I guess if you're struggling with the fractions on these, you could plug it into your calculator, or you could do it by hand. 1/2 plus 1/6 is the same as 2 pi thirds. And then 2/3 plus 1/6 is 5 pi 6. No, I did not do those in my head. I had the problem already written out. And then for the y-coordinate, we want to move up 1, up 1, up 1, all the way through. Okay. So here, I know that I need my graph to go up to 2. So 2, -1, and then I know we need the period of the graph to be to 2 pi thirds. I'm going to do 1, 2, 3, 4, 5, 6 for pi, just because that makes sense with how we had labeled things. We had a lot of 6s in there, so that's a good way to do the graph. Okay, so pi 6 is up at 1. Pi thirds is at 0. Pi halves is at 1. 2 pi thirds is at 2. And then 5 pi 6 is at 1. So there is our shape right there. And then we're just going to continue that shape again. All right. And on this graph, the midline has actually changed, so here's the midline on this one. And then we can still see the amplitude is 1. And the period is from here to here. So even though it doesn't start at 0, it is 4 boxes long, which is 2 pi thirds. Okay, and then that exact same problem, but doing it graphically now. When we do these graphically, I always do them in 2 pieces. So I basically do, I do the parts that have to multiply first. So I do my amplitude and my period change first. And then after that, then I do the vertical or horizontal shift. So for this one, I'm going to go ahead and use 2 different colors. I'm going to do my original with my amplitude change and my period change in pink, and then I'm going to switch it to black for the final answer. So if all I had was an amplitude of 1 and a period of 2 pi thirds, then I know that I would start at 0 and end at 2 pi thirds. And I know that for a sine graph, halfway in between it touches 0 again. And then a sine graph would typically go up to 1 in between these and down to 1 between those. But for this particular graph, it has a reflection over the x-axis. So it's going to go down between these two and up between these two. All right, so there is like my starting point of my graph. And I'm not going to draw that because that's not the actual answer. Now from here, I know that I need each of my points to go right pi 6, which on my graph is 1 box, and they need to go up 1. So I'm going to take each point and move it right 1, up 1. Right 1, up 1. Oop. Right 1, up 1. Right 1, up 1. And then right 1, up 1. So some of those points ended up being graphed on top of the other ones. And there we have the same graph. So algebraically, graphically, it is up to you. Just make sure whatever method you choose is not because it's faster, but because it makes more sense to you and you are capable of doing it correctly.